Good morning, everybody. This is Statistical Computing and Machine Learning. Nicholas Zabaras is speaking. So we will continue the lectures today on the topic of sequential importance sampling. So this is continuation of the earlier lecture on sequential Monte Carlo. So sequential importance sampling and resampling will be one of the key lectures on this topic. So let's see some of the contents for the lecture today. We will review some of the elements of sequential inference that we discussed in the earlier lecture. We will bring to details the sequential importance sampling topics. And then in particular, I'm going to give you an example of what is called the Bootstrap Particle Filter. And I will do that by also reviewing some basic recursive relations for Bayesian inference in state space models. And I'm going to show you how this Bootstrap Particle Filter literally implements those equations. Finally, we will finish with a very brief discussion on how to do simultaneous estimation of the unknown states of the state space model. So these are the states x from 1 to n, but simultaneously also estimating static parameters that maybe define either the dynamical model f that tells us how the states evolve, or the observational model G that gives us the observation Y given the current state X. So the topics today and the objectives include to understand the sequential importance sampling algorithms, and then to understand how to do simultaneous inference of parameters, static parameters, together with the states of the Markov chain. Okay, so let us go and review the fundamentals of the Markovian model that we discussed in the earlier lecture. So this is our state space model. X are the states, Y are the observations, the arrows indicate conditional independence relations. We introduce a prior model that involves a density to sample the initial state x1, and then a dynamical model that tells me how to evolve from the state at time k-1 to state k. And then we had these observations of y1 given x1, y2 given x2, and we consider that those observations condition on the x's are independent. So we had a likelihood model that looks like that. And the objective for the state space model was to literally compute at all times n the posterior of the states x given y. And I remind you, when you see bold x and bold y, those indicate vectors, and the subscripts here indicate, for example, x1 to n is x1, x2, etc., xn. So the objective is to compute this joint filtering distribution P of x1 to n given y1 to n. Now, depending on the application that you may be interested, some simpler problems may come in the picture. So for example, you may be interested in this marginal filtering distribution. So this is only the state xn computed given all the observations up to time n. Or you may be interested at a given time n to do prediction of the next state. All right, so this is P of xn plus 1 given observations only up to time n. Or you may be interested to do smoothing. So these are offline calculations. So let's say you run your model up to total time capital T, and you want to now go back and see if you can get better estimates of the states. So this is the joint smoothing distribution. And more particularly, you may be interested to compute the marginal of xn given all the observations up to time t. So that's the marginal smoothing operations. And as we discussed in the earlier lecture, all of these problems can be answered analytically if we have a linear Gaussian model, and effectively the Kalman filter does that for us. We will not discuss in detail any of those limited cases, but I think I will give you a slide that summarizes the linear Gaussian model and the Kalman filter iterations. So if you want to compare your sequential Monte Carlo algorithms with Kalman filtering for linear Gaussian models, you can do that as well. Okay, so if you remember, we talk about importance sampling. So we assume we have some importance distribution that I denote here as Q of x 1 to n. I remind you, this is not a conditioning notation. It simply indicates that in the selection of the proportional distribution, I want to make it dependent on the observations y1 to yn. We introduce an empirical measure for the importance sampling distribution, so that's our standard Monte Carlo approximation. And then we use this importance sampling distribution to produce an empirical measure for our target distribution, and we use that approximation to come up with approximations for expectations of different functions that depend on the state. So the key equation, I remind you, that gives us the empirical measure for the target distribution. So this is the empirical Monte Carlo measure for the target distribution. The key equation is this, where little w are nothing else but the anormalized weights, and the anormalized weights are basically the anormalized target distribution, which is the joint of x, the distribution of x from 1 to n and y from 1 to n, divided by q, so that's little w. And again, q n hat is nothing else but the empirical measure of the distribution q. So when you plug in this equation the empirical measure for q, effectively what you get is you get a Monte Carlo approximation for the target distribution that is the same delta functions that we had for q, but now they are weighted with these normalized weights. So this is capital W again, and capital W is nothing else but W computed at each of our samples divided by the summation of the W's computed for all the samples. Okay, so these are the normalized weights, and sometimes, I will indicate that capital W is proportional to little w when the normalization constant is not relevant, but in this equation we have to use the normalized weights capital W. We also discuss on how to compute the normalization constant, and remember the normalization constant was nothing else but the integral of the anormalized target distribution. So we had used the name gamma for that, but effectively it's nothing else but the joint distribution again of x from 1 to n and y from 1 to n. So the integral of that in the space of all the states gives us the normalizing constant. So if you can think writing that integral as gamma divided by q times q, and you substitute the second q with the importance sampling distribution, this first ratio of gamma over q will give you the anormalized weights, and then standard Monte Carlo approximations tells us that the estimate for the normalization constant is nothing else but 1 over n, the summation of the anormalized weights computed for each of the samples I. Again, on the bottom it's nothing else but a standard Monte Carlo approximation. This requires literally the ratio, if you like, of two Monte Carlo approximations, and we had discussed all of the above in detail in earlier lectures. So now if you are asking, can I compute the approximations using this importance sampling measure for my target distribution? Can I compute maybe the expectation, some function phi that depends on all the states x1 to xn? The answer is, of course, you can. And here is the importance sampling approximation, nothing else but summation of the normalized weights times this function computed at each of the samples. And of course, we had derived error estimates that you see them written here. I remind you effectively that using the delta method, we have seen that these approximations are biased, and this is the bias that you see here. It is 1 over n times this integral, and the variance is given as 1 over n times this integral here. And I write this in the form of the central limit theorem just to summarize them in a more proper fashion. Now, do not get confused. In earlier lectures, I had written this in terms of the normalized weights W, but easily you can see that those equations are identical with what you see on this slide. All right, I put this explicitly so you know exactly what is involved in computing the bias and the variance for this importance sampling approximation. So, and again, if you look at the mean squared error, that's bias squared plus variance. So the bias square varies as 1 over n squared, and the variance varies as 1 over n. All right, so we do get a bias that we have to deal with. Okay, so we're ready to start now slowly talking about sequential importance sampling. And so again, this is our target distribution. So let me introduce our notation again. I'm going to write the target distribution at time n as pi subscript n, and that again the posterior of x 1 to n given all the observations y from 1 to n. I am writing my target distribution as the unnormalized part of it divided by the normalization factor Zn, and gamma n again is nothing else but the join of x1 to n comma y1 to n. So please remember gamma n and Zn because I'm going to be using those in many slides on what is coming. And again, we're interested at the end of the day to come up with approximations, Monte Carlo approximations in sequential fashion that will allow us to compute approximations to expectations similar to what you see here, where the function phi n is a function of the states x1 to xn. Now we have discussed that somehow, if you try to do this with Markov chain Monte Carlo methods, those calculations will be very slow, and really there is no direct and easy way to compute the normalization constants Zn, and so we have to look for alternative methods, and sequential Monte Carlo is one of those alternative methods. So how is sequential importance sampling going to work, or how is it going to look like? So the key idea is this, right? We're interested to compute this target distribution p subscript n minus 1 at time n minus 1, and then we want to move to p subscript n at time n, etc. And every time there is an additional state that is added to the model, but inference is over all the states up to that time. So the idea here is simple. Can we use all the information we accumulate for learning, let's say, the distribution pi subscript n minus 1? Can we use that? Can we reuse it to compute an approximation, a Monte Carlo approximation for the target distribution at time n? So again, can we do it actually in a way that proceeding from the distribution at time n minus 1 to the distribution at time n, it's actually independent of little n, so that somehow the cost of going, let's say, from time 1 to 2 and time 2 to 3 is the same as the cost going from time 1000 to 1001. So the answer is yes, and that's what we will discuss today. And we're going to introduce sequential importance sampling. And the key idea will be to have a proposal distribution that is defined sequentially, reusing information from the previous time steps. And then also the weights, the importance weights also will need to be defined sequentially. So let me go ahead and start giving you a little pieces of the underlying algorithms. So we're going to assume that, again, that our target is the distribution Pn and as well as the normalization constants Zn. So we start, let's say, at time 1, and we produce some approximation to our target distribution, which is the posterior of x1 given y1, and some approximation of z1, right? Using some proposal distribution that is q1 of x1 given y1. I am not telling you yet what that proposal distribution, but let's say this is a standard importance sampling approximation. So at time 1, we use this proposal distribution, this importance sampling distribution, to come up with approximation for this posterior of x1 given y1, as well as for an approximation of the normalization factor z1. So here is this approximation. The approximation, of course, will be given in the standard importance sampling way. So we're going to have these samples x1, I. All of the samples are coming from the importance sampling distribution Q1, and then we're going to have these weights, that they are normalized weights, the way that we discussed earlier. And of course, the normalization constant would be approximated as 1 over n summation of the weights at W1 averaged effectively over all samples x1i. And I remind you again, what is these anormalized weights? They're nothing else but gamma 1 divided by Q1, and gamma 1 is nothing else but the joint distribution of x1 and y1. It's the anormalized part of the posterior of x1 given y1, and this is my proposal distribution, or the importance sampling distribution. So let's say we have done this, we have some Q1 to sample from, and we produce this approximation with these weights capital W1I. The question is, how do we actually proceed now to do this inference problem sequentially? How do we go to the next time step? So the key idea in going to the next time step is actually to factorize our importance sampling distribution the way that you see in this equation here. So we're looking now at time 2, where our target distribution is pi 2 of x1 to 2. So really our target distribution is the posterior of x1 and x2 given the measurements y1 and y2. So we're going to factorize the proposed distribution at time 2 as the previous proposed distribution at time 1, that's q1 of x1 given y1, plus now some incremental proposed distribution that is a proposed distribution that gives us x2, given all the measurements up to now, and given also the state x1. So here is the key idea. Before, we had sampled from the proposed distribution q1. How about if we reuse those samples? And how about if for each of those samples, we actually produce samples x2 using this incremental proposal distribution q2, and that's exactly the equation that you see here indicates. Okay, so the idea is, again, reuse the approximations you had for q1 and now sample from q2 for each sample x1i as indicated in the equation that you see here. So now with this way we can actually start sampling incrementally using a factorized form of the proposed distribution. But how about the weights? What can we say about the weights? Well, the weights can also be computed very easily incrementally, and here is a simple indication of how we can do this. So remember, the weights are nothing else but gamma 2 divided by q2, all right? I'm writing here gamma 2 explicitly, and this is the factorized form of my the proposal distribution as I discuss it here. So what I do is I multiply and divide by the joint of x1 and y1, and in particularly I divide and multiply by the previous joint distribution, or a normalized target posterior at the previous time step. So this is p of x1 comma y1, p of x1 y1. And immediately you can recognize this first term to be the normalized weight. This is the unnormalized weight W1 at time 1. And then we have these incremental weights that are given by this expression, okay? And I'm not going to simplify at present, but you notice here I have the joint distribution of x and y at time 2. This is, I have the joint distribution of x and y at time 1. And here there is only the incremental proposed distribution Q2 of x2 given all the measurements and given x1. Can I actually generalize this, from time step, let's say n-1 time step n? The answer is, of course, I can do this. So I am going to factorize. Let's say that we have this previous proposal distribution at time n-1, all right? So to come up with a factorization for the proposal distribution at time n, I'm going to take everything I had produced before at time n-1 plus this incremental proposal distribution that gives us xn given all the observations up to now and given all the states up to time n-1. Okay, so effectively what you can do is take all the samples that you produce up to time n-1, and the only thing you have to do is you will actually have to produce samples for the state xn. And how do you do this? You do this by sampling from the incremental proposal distribution, as you see on the equation on the bottom. So these are the samples that we computed up to now at time n-1, and then for each of those samples we now produce a sample xni by sampling this incremental proposal distribution Qn of xn given all the observations up to time n and given all the samples that I had in my approximation up to time n-1. Okay, so that's very easy, right? So the idea is we factorize the proposal distribution so we can reuse the previous samples, and then we move those samples from one time step to another, producing approximations, importance sampling approximations for our target distribution at each time. And I can do the same thing with the weights. Again, I can write the weights in an incremental fashion, and the trick is again the same as before. What I can do is I can, in the definition of the weights, I can multiply and divide by the joint distribution at the previous time, and immediately you can recognize the first term to be the anormalized weights at time n-1, so I'm going to reuse those, they're not being wasted, and then I have these incremental weights, and you notice again on the bottom here there is only the proposal distribution that allows me to move my previous samples at time up to time n-1 to the samples at time n. And again, I have written this equation as a function of my samples, because this is how I will need to use this to do Monte Carlo approximations, compute approximations of expectations of various functions and the like. So obviously this looks to be very straightforward, right? So the weights are computed in an incremental fashion, and again, these are the anormalized weights, but if you sum all of these weights, you can easily normalize and produce capital W subscript n I. And if I can actually simplify this for our state space model to see how things can look very easily, do you remember how this joint distributions of x and y looks like, right? So this is the probability of the initial state, and then you have the product of all the transition probabilities from x1 to x2, from x2 to x3, etc., and the product of all the observations of y1 given x1, y2 given x2. So if you plug in those in here and you plug in those in there, what actually you get, many terms will be cancelled, and what you left is you left for with the transition model from xn minus 1 to xn, and then you left for the observation with the observation model that gives you yn given xn. So the anormalized weights then can be computed from the previous weights at time n minus 1, and the incremental times the incremental weights that involve f times g divided by this incremental proposal distribution that allows me to sample xn superscript I. Now obviously I can do the same type of approximation, right, for my, so if I look at my target distribution, this is the posterior of x from 1 to n given y 1 to n. I can use all the equations that I had before, and I can do the same thing from the normalization factor z. I can write this with this approximation, but now what is key, what is different from what we had before, the weights are computed incrementally, and even more importantly, the previous samples at time n minus 1 are reused, and then I move them to time n incrementally in a way that somehow makes the cost of going from n-1 to n independent of little n. Okay? Now, with these approximations, of course, you can understand that somehow, as a minimum, you have to keep track of your previous weights, right? And you may also have to keep track of all the previous paths that you sample up to a given time. Okay, depending, of course, on the application that you have in mind. All right. So we have a nice, incremental way to compute, to sample from one step to the next. We have a nice incremental way to compute the weights. So what are the degrees of freedom that we have in the problem? All the degrees of freedom have to do with the choice that you see here in this proposal distribution. So all the approximations and the different ways for doing sequential Monte Carlo is what you actually do with respect to this incremental proposal distribution. So I'm going to show you with a rather simple equation that the optimal proposal distribution is actually nothing else but this conditional that you see here at time n. So it is basically the conditional of xn given all the observations up to time n and given all the states up to time n-1. And you can actually easily see that this optimal distribution that minimizes the variance of the weights of my importance sampling approximation can be computed by looking at the incremental weights. And remember, the incremental weights involve the ratio of the joint distribution at time n divided by the joint distribution at n-1, divided here by the incremental proposal distribution. So what I do is I use the product rule in the numerator, and I write this joint distribution as this conditional times the joint distribution of x and y, where x is from 1 to n-1 and y is from 1 to n. And now you notice the only place that I have xn is in this term here. So obviously the importance sampling, the incremental importance sampling distribution that minimizes the variance of the weights is the one that is equal to this conditional of xn given all my observations up to time n and given all my states up to time n-1. So if this, in this optimal case, this will cancel out, and what you get is this joint distribution divided by this joint distribution, and actually literally you can observe that the numerator is nothing else but the unnormalized distribution gamma n, but with xn marginalized, integrated out. There is no xn here. So here what I have is, I have this normalized, I have this marginal gamma n, where xn has been integrated out as indicated in this equation, divided by my joint unnormalized posterior at time n-1. Now, there are two problems, of course, with this optimal incremental importance sampling distribution that minimizes the variance of the weights, and the problems are, first, this distribution may not be easy to compute, all right? So condition on all of this information may be something difficult to evaluate, and then secondly, you can see immediately here that computing this incremental weights requires this marginalization that may not be also easy to do. So what we will need to do is we will need to come up with something that looks close to this conditional distribution, but effectively it is some approximation of this optimal proposal distribution that we discuss on the slide. So we do need to have some sort of approximation, and different approximations, of course, will give us different sequential Monte Carlo methods. All right. Let me summarize where we are, right? So up to now, effectively, we have resolved problem 2 that I referred to in the previous lecture. And problem 2 was being able to go from one time step to the next with a cost that is independent of n, right? So we actually have sort of solved that problem, okay? So we have complexity that we can control as we move from one time step to another. However, there is a problem, and the problem here is that the variance of the weights unfortunately increases with time, and it increases actually exponentially with time. And this problem is particularly significant because what we get what is called weight degeneracy, because after some time we will actually be left only with one weight that has a non-zero value. All right. So the idea here is we're going to have to do something with this weight degeneracy and the fact that the variance of the weights increases exponentially with time. Otherwise, the fact that the computational cost is constant independent of n doesn't help if the variance of the weights goes to infinity. So the problems basically with this variance for this high dimensional Bayesian estimation problems, the fact that the variance goes to infinity is nothing different from what we have seen with importance sampling. I mean, you cannot expect anything different because we discussed importance sampling and we mentioned that importance sampling actually fails in high dimensions. And the only way that we differ from standard in importance sampling is that we factorize our importance sampling distribution the way that we discussed in the last few slides. So beyond that, there is no other reason to expect that somehow we will have the variance under control, because still we do standard importance sampling with some sort of nice, hierarchical or incremental proposal distribution. So we need to address this problem. And before we do that, I'm going to give you an example that I will repeat, I believe, in the follow-up lecture to indicate to you on how this issue will be resolved. But let me remind you the same example we did for importance sampling. This goes back several lectures when we discuss importance sampling. So I'm going to do the same example once more to show you that the variance of the weights increases exponentially. So let me see what that toy example would be. I'm going to take that my target distribution is basically the product of this standard univariate Gaussians. So my anormalized target distribution at time n is nothing else but this, okay? And the normalization constant Zn is 2 pi to the power n over 2. So I'm going to use a smart proposal distribution or importance sampling distribution, and that distribution is also going to be a Gaussian, factorizing the same way as before. But now I am going to take the variance in these univariate Gaussians to be sigma squared, where I'm going to take, and you will see why, that sigma squared is different from 1 and is greater than 1/2. So again, my importance sampling distribution will look like this, right? And you can actually think that you can choose sigma squared so that this distribution is very close to your target distribution, so you anticipate this to work, but actually, as we will see, it will not work because it will lead to a variance that increases exponentially with n. So let me do the calculations, and I think this will actually help us also to see some of the details of sequential importance sampling. So what I'm going to do is I am going to take the weights. These are the anormalized weights. Just so the notation is not confusing, I am using a subscript sigma to indicate that basically my importance sampling distribution is a function of sigma squared. So you can actually play with different values of sigma squared. But apart from that, w, little w is gamma n divided by qn. So if you plug in your values for gamma that you see here, if you plug in your values for q that is here, you get something like that. And you can see that these weights are bounded, but if, of course, sigma is greater than 1, right, this, as n goes to infinity, this bounded constant becomes huge, so this inequality is no help. But apart from that, let's start computing the variance of these weights, right? So I'm writing this variance explicitly. You plug in your Q, your W square, you integrate things, and this is what you get at the end of the day, right? You can please follow the algebra. All the details are typed in the slide. So the variance of the anormalized weights for this particular importance sampling distribution is given like this. So let's see now what happens. If I divide by Zn square, which is the normalized constant square, so I can get rid of this term, and then I have the normalized variance of here I'm writing this is the variance of Zn divided by Zn square, but I remind you that the variance of the normalization constant of my target distribution Z, right, is 1 over n times the variance of the weights. And so the only difference of this equation from this equation is I take this and I divide by n to get the variance of Zn. Okay? And then I pull this 2 pi to the power n to the left-hand side. So here I have the normalized variance of the normalization constant. It's much more compact way to write down the relevance of this, the variance of the importance weights. Okay, so that's the normalized variance of my normalization, of the approximation to the normalization constant. Now, you can easily see that with these assumptions that we did on sigma square, and we can do anything we want to, that sigma to the power 4 is greater than 2 sigma square minus 1, which means this is greater than 1 and it is to the power n over 2, which means that the normalized variance for Zn, and of course by extension the variance of the weights, they go to infinity as n goes to infinity. So effectively we have an issue, right? For this high dimensional problem, as n goes to infinity, the normalized variance for Z, for the estimation of Z, as well as the variance for the weights, they go to infinity. As a matter of fact, let me give you a specific example. If you choose sigma squared to be 1.2, you can actually appreciate that the proposal distribution is very close to the target distribution that has sigma squared is equal to 1 basically. And then for this value of sigma squared, you can compute n times the normalized variance of Z to be 1.1 to the power n over 2. So if you plug in the values for sigma in this expression, you get 1.1 to the power n over 2, and for n equal to 1,000, so if you do 1,000 times steps, n times this normalized variance comes to be 1.9 10 to the power 21. And you know what that means? Means that if you actually want this normalized variance to be, let's say, 0.01, which is a reasonable expected value for a good approximator, then the value of n that you will need to achieve this is of the order of 10 to the power 23. So you're going to need basically 10 to the 23 Monte Carlo samples to drop the normalized variance for Z to the order of 0.01. That's obviously highly unrealistic. So we have a problem up to now that somehow we need to address. Okay, and I can tell you so that you know what is coming. One of the ways that this is going to be addressed will be by introducing this concept of resampling from the approximations that we already have discussed up to now. So we will see this in some detail in a few slides. Okay, so let me before I address how this variance issue can be resolved, let me give you some typical approximations that we use for the incremental proposal distribution. And the most typical approximation is rather to this equation that you see here. So you say, look, in estimating xn, I don't really need all the observations and all the previous samples. I'm very happy to use my current observation and my state at n-1. So that's a sensible sort of approximation. You can say that you don't bring any further information, keeping all the previous observations and all the previous states, and yn and xn-1 is good enough. That, of course, simplifies a lot. The importance sampling distribution at time n will be the importance sampling distribution at the previous time times this incremental conditional distribution of xn given yn and xn minus 1. I want to emphasize that here you notice I have kept the observation because the observation has a lot to do with the optimal choice for xn, so this is very, very important. So the previous algorithm that we discussed remains the same. We're going to assume that we have samples time n-1 that you see here, and for each of those samples at the previous time, we're going to sample the conditional distribution that you see here to move those samples to time n. So effectively what we're going to have is we're going to have a sample path that consists from the previously sampled paths, and then we will only sample a single component at time n. So the cost of sampling or producing Monte Carlo approximation at time n is going to look the same as I go from one time step to another, because effectively we are reusing all the previous samples at the time n-1. Okay, the approximation, still with this new incremental proposal distribution will not look any different from what we had before. So I'm just summarizing those equations that we have seen before. And I have also given you the incremental weights. You remember they were just my dynamic model f of xn given xn minus 1 times the observation model at time n. And the incremental proposal distribution is this simple q of xn given yn, comma, xn minus 1. So here is how the overall algorithm is going to look for this particular case of this incremental proposal distribution. So you start at time 1, you sample from the proposal distribution x1 given y1, you produce an approximation to your target distribution, and you notice here in the weights, in the general formula that we had in the previous slide, I had the dynamic model, but obviously at time 1, I don't have anywhere to transition. I only have my distribution mu of x1, so this will come here, times the observation model at time, and this should actually make it y1 conditional on x1, okay, y1 conditional on x1. So that's what I have at time 1, and then you can repeat these calculations now at each time n, reusing your previous samples that you see here, and reusing your previous weights, and then calculating the incremental weights, and of course sampling x and I using your samples at the previous time step n-1. So rather straightforward, and again all these calculations are independent of n, but again I remind you, none of this addresses yet the problem with a variance that explodes. Okay, so we're going to need to come back to that. So you can actually try various proposal distributions and various approximations for this Q that you see here. They're not going to help eventually all of these approximations. They're going to have this variance problem. So the algorithm that you just saw that goes with the name Sequential Importance Sampling gives you a computational cost that effectively It's independent of little n. It's extremely easy to parallelize. It reuses both the previous samples as well as the previous weights to produce an importance sampling approximation at time n. And if, let's say, you are only interested in the marginal posterior of xn given your observations up to time n, you can do this very easily. And here is the approximations that you need to do. So the incremental weights are basically identical to what we had before. These are the weights at time n minus 1. The only difference in producing this marginal of xn given all my observations up to time n is effectively that in my empirical distribution in these delta masses, I only have samples xni, okay? Which actually, in principle, it means looking at this algorithm that somehow you don't have to keep track of all the previous paths if you only know the samples at time n minus 1, then you're good to go in this type of approximations. And of course, theoretically speaking, right, that this type of approximations, that's important sampling, you can show that you converge as n goes to infinity to the true target distribution. But again, we have that issue with the variance that still needs to be addressed. So before we go there, let me give you a very drastic approximation for the proposal distribution, for this important sampling distribution. And this very drastic approximation identifies a very particular algorithm that goes with the name the Bootstrap Particle Filter algorithm. So what is this algorithm? The algorithm says select as a proposal distribution of time n to be nothing else but the prior model of your states, right? So Q of x1n given all your observations is only the prior model of the states x1 to xn. So immediately you can see there is no information from observations coming in this choice of a proposal distribution. So you don't anticipate this model to be able to do very well, but obviously it's a very simple model because look what happens. When you compute the incremental proposal distribution, so going from n minus 1 to n, that is the ratio of the proposal distribution from our factorization at time n divided from the proposal distribution at n minus 1. This is the joint distribution of all the states up to n. This is the joint distribution of all the states up to n minus 1. And if you plug in this to be mu of x1 times f of x2 given x1 times f of x3 given x2, etc., and you cancel many terms out, it comes out that this incremental proposal is nothing else but f of xn given xn minus 1. And why is that important? Because immediately when you look at the anormalized weights, if this incremental proposal distribution is equal to f, this cancels out, and the incremental weights become basically your observation model at time tn. As a matter of fact, if you do this recursively, right, you can immediately guess that the weights at time n, when you multiply all of this, they're nothing else but the product of your observations, of these observation models of g of yk given xk. So effectively, in this Bootstrap particle filter, we simulate following our dynamical model. This is how we move particles from time n minus 1 to time n. And the weights, we increment them by multiplying them with the observation model G. So very simple model. And if you look for the particulars of this algorithm, if I can put this whole thing up, this is how the algorithm looks like, all right? So you start at time 1, you sample from your distribution that defines state 1, you compute the weight W1, and then to proceed from n minus 1 to n, what you need to do is keep your previous paths, right? Sample x1 given the particle xn minus 1i, all right? I can actually simplify this because this only depends on xn minus 1i. The incremental weights require nothing else but multiplying your previous weights by the observation model. You can normalize, and then you're done, right? So all right. So, by the way, I just noticed looking at this equation here, you may say, why are you sampling here from this proposed from mu? Remember, mu is the density that defines the initial states. You remember our proposed distribution is the prior of the states, and the prior of the states at time 1, the prior of x1 is mu of x1, and that's why you see here that I am sampling from mu. Okay, so if you try to compare this with previous slides where I had sampling from q1 of x1 given y1, that q1 of x1 given y1 in this particular case becomes equal to mu, because that's my assumption for the Bootstrap particle filter. So at the end of the day, basically I get samples that I can approximate my target distribution at each time. Now, let's start talking a bit about the degeneracy that I mentioned before. So it turns out that if you apply this algorithm as is, both the generic algorithm as well as the Bootstrap particle filter, effectively at some time and after that time, all the weights are going to become 0, and you're going to be left actually with only one delta function, and I denote here this delta function for a particle I0. So here this particle is going to have weight 1 because these are normalized weights W. So all the weights die, and only one sample remains with weight equal to 1. So we're going to have to do resampling to address this degeneracy problem. And the idea of resampling is very simple. When the variance of your weights is very high, the idea is to kill some samples that have very low weights in comparison to the standard 1/n Monte Carlo weight, and then multiply the particles that have higher weights. And why this is a good idea? Because if one sample has a low weight, let's say at time n-1, the way we define the weights from one time step to another incrementally, you anticipate that that sample is going to have an even lower weight at the next time step, and then at the next time step. So the idea is we will kill that particle, and we will actually multiply the particles that have higher weights. So this is what the idea of resampling is that we're going to apply. Okay. Now, resampling is going to at least partially address the degeneracy problem of the sequential importance sampling algorithms, and the fact that for these high dimension problems, eventually the variance of the weights goes to infinity. So let's see what this resampling algorithm is and how actually it can be used for our importance sampling approximations. So let's say we computed a Monte Carlo approximation for our target distribution at time n that is given by this equation, the way that you see here. So what I'm going to do is I am going to sample with replacement from this empirical distribution. And I'm going to sample with replacement in proportion to the weights, to these normalized weights that we computed already. So, the idea here is when you look at this empirical approximation, some samples have very high weights. So there will be a higher probability that I'm going to resample those multiple times. And some samples have very low weights. So there is very low probability that I'm going to sample those at all. So some samples may never be sampled again. Okay? So I'm going to sample with replacement from a categorical distribution with parameters that correspond to these weights. And then here are the new samples from this empirical distribution. and then the new approximation I'm going to get unweighted samples in the standard Monte Carlo way that will give me an approximation that is the one that you see at the bottom of the slide at this time. A little bit about the notation, and I know it's a little bit awkward even for me. I try to use p hat to indicate the Monte Carlo approximations we get with weights, okay? Simply because this is the notation we used up to now. And then when we resample, I use a tilde on the top of the distribution to indicate a resample distribution, so that immediately reminds you a standard Monte Carlo approximation, and I use x tilde also to indicate the resample samples. So the idea here is these samples here, x tilde, they are all of them coming from this samples x1n superscript I. But not all of the samples are surviving, so this includes copies of some samples that come with high weights, so maybe you can have 3 or 4 times the same sample, and then it does not include some other samples that have smaller weights. I'm going to give you an equation actually that hopefully will clarify this even better, but right now let me just mention that you have to be very careful when you try to do sort of error approximations or write central limit type of error calculations using this resampled empirical measure. And the reason for that is you cannot really do CLT approximations using this empirical measure. And the reason for that is that these samples x tilde, they are not really independent. So as I mentioned, right, you maybe some original sample that had high weights, maybe you sample it 10 times. So obviously you don't anticipate that you will be able to write down CLT type of approximations. They are not holding for these resampled distributions. Okay, so this is the key idea of resampling, and of course we will discuss further this shortly. And what I'm going to do is I'm going to try to give you in the lecture today some details of this resampling process for the Bootstrap Particle Filter. And because the Bootstrap Particle Filter, it actually implements some fundamental recursion formulas for the state space models, I wanted to bring those in the lecture today as well, okay? And then I will put everything together before the lecture. All right, so let's review what these fundamental recursions for the state space model are and how the Bootstrap Particle Filter actually implements those. And then let's discuss again these resampling approximations for the Bootstrap Particle Filter. So let me, I'm going to write all the equations first down for this filtering and marginal likelihood approximations. So what I want you to do is I want you to concentrate on the 2 steps on the bottom of the slide, okay? So the idea is I want to build a recursive manner that will allow me to go from my target distribution at time n-1, that's this distribution, to my target distribution at time n, which is again the posterior of x1 to xn given all my observations up to time n. So I want to do this again incrementally, and here we're going to write things not with weights and particles the way we had before. I'm going to write this directly in terms of densities. So to go from the previous target distribution to the new target distribution, I need to do 2 steps that these 2 equations that you see here summarize. One is to do a prediction 1 step ahead using all of my observations up to time n-1, and you can see this prediction step is nothing else but using my previous target distribution times my dynamical model going from n-1 to xn. So I'm predicting 1 time ahead using my previous observations, and then now with this prediction I need to do an update, and the update here implies if I suddenly observe also the measurement yn, can I say something better about the posterior of x1 to n? And the answer is yes. The answer comes that is basically proportional to this prediction that I had on step 1 times the observation model. So these equations are extremely simple, right? And in some sense, you can anticipate that they will look the way they do, right? So you start with this, you want to make a prediction, you use your dynamical model. That's the easiest way to think, and that's what it comes out in this recursion. And then if you want to update when you have an observation yn, you simply multiply it by g of yn given xn. And then, of course, there is a normalization factor here that is given by this equation that I will discuss shortly. Now, what you need to know is the two equations on the bottom, but let me tell you, let me highlight the proof, because the proof is not magic. It's a very simple proof. How do you compute these updates? So let me, this is my target posterior, right? So I repeat this by writing it as the joint distribution of x and y divided by p of y. And then what I do is I multiply and divide by the target distribution at n-1. The only difference is that on the bottom, I write this target distribution at n-1 as the joint divided by p of y from 1 to n-1. And why I do this? Because then my target distribution can be written in a very simple form. It can be written as the ratio of the target distribution at n divided, these are the unnormalized, right? This is the unnormalized distribution at time n divided by the unnormalized distribution, the joint at time n-1. Then I have this marginal ratio, and then I have my target distribution at n-1. Now, you look at this, and you know from your state space model, when you explicitly plug in terms and you cancel lots of terms up to time n-1, what you get is you get basically the observation model at xn given x-1 times, this is the dynamic model xn given xn-1 times the observation model of yn given xn. And then what do I have here? This is nothing else but the conditional of yn given y from 1 to n-1, right? So this ratio is this weird looking conditional of the observation at time n given all my previous observations, and then this is my target distribution at n-1. So the recursion that I mentioned on the bottom of the slide, immediately you can see it, because if I put all of this together, this terms here, f times this previous target distribution, they are nothing else but my one step ahead prediction that I mentioned in step 1. And then when I multiply this by g, it gives me basically the update. It gives me the target distribution of x1 to n given y1 to n. And of course, there is a normalization constant that somehow you need to compute as well. If you're interested to see how that normalization constant comes in, it's actually not very difficult. This is what you need to compute. I can write this as the joint of yn and xn with xn marginalized. I can, keeping this conditioning constant, I can write this as yn given xn and this, and there's no dependence of yn beyond xn, so I get g of yn given xn times p of xn given y1 to n-1. Actually, I can stop literally here, and I think I will use this equation in follow-up slides, because this is the one-step prediction, right? One step ahead prediction. But if you want to write this directly in terms of the target distribution at time n-1, what you can do is you can plug in an n-1 and integrate also n-1 out, and then you can get this nice expression that involves the observation model at the current time, the dynamic model at the current time, and then this distribution, it is the marginal filtering distribution at time n-1. You remember, we have this at time n-1. If we have that, we actually have an approximation for the marginal of xn-1 given the observations of at all the previous time steps up to n-1. So summary, right? I can go with these equations from the target distribution at n-1 to the target distribution at n in two steps. First step, one step ahead prediction. The other one is an update using my observation at time n. Now, these are the same equations summarized here, and I actually give you those equations in terms of the marginals, all right? So they may look slightly different, but they are exactly the same equations. They are the marginal versions of the previous equations. So they give you the prediction one step ahead, okay? So of xn, which is the equation that I had before, okay? And this is, again, the marginal filtering distribution at n-1. And then, of course, I have the update when observation yn comes, which is the product, basically, of z times the one step ahead prediction that I computed at step 1. Now, the nice thing is, if your model is linear Gaussian, so if these functions f and g fit in that category, all of these distributions and whatever integrals you have seen in these last few slides can be computed analytically, and all of these things lead to the Kalman filtering equations. And so again, I am going to give you those equations somewhere down the lecture, but somehow this recursive equations, all right, would be very useful to see and motivate yourselves on how the Bootstrap particle filter is coming about. But generally speaking, in the context of sequential Monte Carlo, they're not necessarily that useful. Okay, but I wanted to make a link of the Bootstrap particle filter with these recursive equations to see that the Bootstrap filter effectively implements these equations directly for the general nonlinear, non-Gaussian state space model. So before I show you this, let me mention the following. If you're interested in the marginal distribution of the y's, so if you're interested on this marginal distribution, you can actually recursively compute this like this. Here I'm not doing anything but using, this is the product rule, right? So this is, you know, P of y1, y2, etc. is P of y1 times P of y2 given y1, P of y3 given y1 and y2, etc. And this conditional can be actually computed very easily using our previous distributions. And I'm going to go directly to the final result because it's very easy to follow the calculations. So if you want to compute this distribution that comes here in this factorization, what you need is you can use this expression that is given here that involves the observation model at time k and the one step ahead predictive distribution that I gave you a recursion before, or you can use this blue equation here on the bottom where you use both the observation model and the dynamic model and the marginal filtering distribution at time k-1. Notice here there is an integration on the states xk-1 and xk. Here the integration is only on xk. But one way or another, we can actually compute this marginal likelihood as a product of low-dimensional terms, and all of these terms don't require anything but the target distributions that we have seen as our main focus for the sequential Monte Carlo approximations. Okay, so let's go to the Bootstrap particle filter, all right, and see why it is a natural extension and implementation of these update recursive equations that we discussed. Let's assume that at time n-1, I have a Monte Carlo approximation for my target distribution, which is the posterior of all the states up to n-1 given all my observations. And the only thing I am going to emphasize here is that I assume that I have done resampling at time n-1, right? So I have written my target distribution at n-1, using this resampled tilde of x, okay? So, so apart from that, there is nothing else, right? So I basically got rid of the weights, okay? I got rid of the weights by by resampling, okay? And I have this know now, we assume we know this at time n-1. And the question is, what is the Monte Carlo approximation of my target posterior at time n, all right? How can these recursive equations can be used to actually compute an update? And so here is the key idea. We're going to use the particle I at time n-1, and we're going to resample from our dynamical model. So we're going to take now these new sample particles and our previous paths, all right? And we're going to use the predictive distribution, the one step ahead predictive distribution that I remind you is nothing else but the dynamic model times the previous target distribution at n-1. So what I'm going to do is I'm going to take this approximation that I had at n-1, I am going to plug it in here, and then what I'm going to get is I am going to get a Monte Carlo approximation for my one step ahead prediction. So this is the one step ahead prediction of x1 to n, where I reuse all my previous samples and I move them in time to sample x and I using my dynamic model the way that you see here. So effectively, this update that I had before, right, this update that I had before effectively implements this sampling from the dynamic model, all right, simply because of the form that I have in this equation. If you plug in here this empirical measure, you effectively get exactly what, the way we sample things in the Bootstrap Particle Filter. So, of course, our target distribution is not just the one step ahead prediction, but our target distribution is the conditional of x1n given y1n. And I remind you the recursive formula that I had before. If I don't pay attention for now to the normalization constant, what I have here is g of yn given xn times the one step ahead prediction. The normalization constant is actually nothing else but g of yn given xn times this one step prediction with an integral in xn from the previous slides. So what I'm going to do is I am going to use the Monte Carlo approximation I produced on the previous slide for this predictive distribution. So I'm going to plug it in here. I'm going to plug it in also in the numerator. And guess what you get when you do all of the above? When you do all of the above, actually, you do get your bootstrap approximation for our target distribution at time n, which is the ratio, which is basically these normalized weights. And the normalized weights are basically g of yn given x and I divided by this normalization constant, which is the sample, which is the sum of all the g's evaluated for all the samples I at time n. So the idea is, we discussed before the incremental way for doing importance sampling, and we said the major approximation in Bootstrap particle filtering is to make the incremental proposal distribution to be my dynamical model F, and then the weights were turning up to be the observation model G. And you notice here when I use my recursive equations, I get exactly the same equations as what we have seen several slides ago when we introduced the bootstrap filtering. All right, so now we are ready to actually spend a little bit more time to discuss about the resampling process, because all of these are good, but somehow they don't work because the variance of the weights is going to blow up. So what we're going to do is we're going to have to resample. So let's say that at time n I have a Monte Carlo approximation with this capital W weights of my target distribution. So what we will do is we're going to sample from this distribution in proportion to the weights, all right? And I will call the new samples tilde of x, all right? Tilde of x will come from this empirical measure. And I'm going to come up, if I do this with a new approximation, and I'm writing this new approximation now in two different forms to facilitate of your understanding. So let me first look at this expression here. These samples that you see here, x1 and I, they're the same as the samples that I had in my original approximation before resampling. But what is n subscript n superscript I is basically the number of times this I sample is going to be sampled. And as you remember, some samples will be sampled many times, and some other samples will never be sampled. So if you want to rewrite this only in terms of the samples that come out from this resampling process, so if you want to get rid of everything that has been killed, these are these tilde samples x that you see here, and this is the Monte Carlo approximation that we use, where basically the weights are equal to 1 over n. Now, since we're using a categorical or a multinomial distribution to get these samples, this number of times that you will sample, particle I, all of these things follow a multinomial distribution, so you can write that the expectation of nn for particle I is given n times the weight for this particle at time n, and the variance is n times w1 minus w. Where these formulas come, you can actually click on Wikipedia and see the expectation and the variance for the categorical or multinomial distribution. You will see where those things come from. But for now, what I'm going to do is I am going to use this approximation with tilde implying resampled, this resampling process. So not all of the samples x that you see here have survived here, right? So here includes only the samples that have survived, and some of those samples appear multiple times, right? A sample with high weight in here maybe will be sampled 50 times, and so this will come in this approximation. Now let's see in a little bit more detail how we're going to do this resampling, okay? And so I mentioned we're going to sample in proportion to the weights. So imagine that in your original distribution you had weights multiplying these delta masses corresponding to different samples. So if you sample a categorical distribution in proportion to the weights, okay, the first thing you're going to do is you're going to sample some indices, and these indices will actually tell you which particles you're going to propagate to the next time step, okay? And I indicate this with this equation like that, all right? So these are the particles that you're going to propagate to the next time step, and the index that I use here, which is the same index that I sample from the categorical distribution, emphasizes that this particle here is the ancestor of the particle at I at time n. Okay, look at the notation again. This particle here at time n minus 1 is the ancestor of the particle at particle I at time n, and I denote this as such. So the idea is when you sample from the categorical distribution, that will give you these ancestor indices, and for each of these indices, the corresponding particle will actually propagate to time n, and it will give you an offspring at time a. And this is how this resampling process works. So what we have seen here is we have seen these indices that we sample that define which particles will propagate. So these are the ancestor indices. And you notice these ancestor indices are random variables to emphasize that this resampling process is by its nature stochastic, all right? And obviously these ancestor indices allow us to keep track of which particles to propagate, but more importantly, they allow us to keep track of the ancestor paths, right? So every particle comes from some parents, and those parents come from another particle, and that particle comes from another particle at the previous time. So these ancestor indices help us to keep track of these ancestor paths. So let me summarize the algorithm. This is again for the Bootstrap Particle Filter. You sample a time 1 from your distribution mu of x1. Remember, that's your proposal distribution. Okay, so you come up with an approximation of your target distribution at time 1 in terms of these weights. Okay, you're going to resample, and the samples are x tilde 1. So this is your new Monte Carlo approximation. And now we're going to go from n minus 1 to time n. So you're going to assume that at time n minus 1 you have this weighted approximation that looks like this. So we're going to need to produce now an approximation at time n, and we're going to do this in steps. Step 1, we're going to resample these ancestor indices to figure out which of these particles to propagate to the next time step. We're going now to define this new samples tilde of x. So we're going to kill whatever samples are not going to be selected in the resampling process. So this is the resampling process. Then we're going to the particles identified by these indices, we will propagate them forward using our dynamical model, and the new path will be the previous paths, right? And you notice here I use x tilde because this includes only the paths that survived after resampling at time n minus 1. I'm going to show you this schematically shortly, right? But these are the paths that have survived up to time n minus 1. And then I add also the x and I, at time n. So what you see here is effectively I have produced an approximation for the one step ahead predictive distribution of x1 to n given my observations up to n minus 1. And then of course you're done. The only thing that is left is to weight these samples, these new samples, and you weight them in proportion to your observation model at time n, and that gives you the Monte Carlo importance sampling approximation at time n. So you can see how I started with this weighted approximation at time n minus 1, and I produce a weighted approximation at time n. And again, pay attention to the notation I use. X tilde indicates the particles that are going to propagate to the next time step. The rest of X particles have been killed. The new paths have been defined from the paths that survived at n minus 1 after resampling, plus the new location of the particles x and I. All right. This is when I take my particles that survived at n minus 1 and I propagate them forward, right? So this particle is the ancestor of x and I, and this is my Monte Carlo approximation of the one-step look-ahead predictive distribution, and this is the Monte Carlo approximation for my final target distribution, the posterior of x1 to n given y1 to n. So let me do one graphical example, right? So I'm going to take that there are 3 particles here that, and I look at 3 times. I'm going to call this time 1, so that's the subscript, time 2, time 3. And at each time, I'm going to keep n equal to 3, okay? Now, the locations of the particles is given here. Not to be to confuse you, they don't supposed to be looking to be next to each other or on the same location, right? On the same, let's say, vertical axis. So if these samples are anywhere, but the idea is I have 3 samples here, 3 samples there, and 3 samples to start with. All right, so what you see here is you see the resampling process at time 1. So I start with 3 samples, and you notice the sample 2 is going to be resampled twice, all right? And sample 3 is going also to survive, is sampled once. So in the next step, I will move twice the sample. So one time it will generate an offspring that is this sample here, all right? It will generate another offspring that is this sample here, and then this sample, it will generate an offspring which is here. So I generate 3 samples. Now at time step 2, of course, you calculate the weights, and you resample again in proportion to the weights, and it turns out that this sample was resampled once, and this sample here was resampled twice, so this will give us 2 offsprings, and this will give us 1, and then I have 3 offsprings, 3 samples, exactly as we started, as we started. So we have 3 samples at each time step. There is a resampling process that I have applied at time step 1, a resampling process at time step 2. And the particle terminology that you see here, it is actually the terminology before resampling, okay? I prefer to use these tilde effects to indicate the samples after resampling. So let me concentrate on this particle and trying to find out its ancestral path, basically to find its first ancestor and then the ancestor of this ancestor. So let's see how we're going to do this, and we're going to do this using 2 versions, if you like, of our previous notation. So you remember before, I defined the paths to be the previous resample path and the new location of the particle at time n. So if I look now on the ancestral path of the particle x13, so this is my first particle at time 3, all right? I am going to have to find the path that terminates to a parent that leads to this offspring. And you can see from this picture that the particle that actually through the dynamic model leads to x13 is nothing else but x22. But you notice I indicate here as tilde of x at time 2 with superscript 1 to emphasize that's the first sample that was resampled at time 2. So effectively, I keep, the superscript 1 here and the superscript 1 here. The idea here is that my first resampled sample at time 2, that gives me an offspring x13. And similarly, this particular sample x22 comes, if you look at its ancestral path, comes from it's one of the 2 offsprings. So the parent is x12. This is what I indicate here. But if you want to use a tilde notation for this particle, you notice the tilde notation will be tilde of x subscript 1, so it's particle 1, time 1, but particle 2, because this particle was sampled twice, all right, during the resampling process. So I have 2 copies of this particle. One copy gave this offspring, and the second copy gave x22 as offspring. So I write this as tilde of x at time 1 superscript 2. So anyways, what you have here is the ancestral path, and again, you need to have some understanding of what this notation means like, and if you don't like that notation, another alternative way to actually look at this is as follows. So this is the particle x and I, and this is the ancestral path of that particle. So effectively, this ancestral path here terminates at the ancestor of x and I. And what does it mean, the ancestor of x and I? Is the particle at time n-1 through which through the dynamic model gives us the particle x and I. Okay? So again, this defines the ancestral path of x and I, and that ancestral path at n-1 ends at the ancestor of x and I. And what is the ancestor of x and I? Is the particle at n-1 that through the dynamical model transitions to x and I. You can see here, if you look, this is the ancestral path of this particle x13, and the particle that is the ancestor of x13 is of course x22. And I'm not using a tilde here, so the notation that I have here using ancestor indices refers to the original particle notation before resampling. So again, to confuse you even further, if you want to define this whole ancestral path of the particle x13 using ancestral indices, this is how I am going to write this. Okay, so what is this notation here, right? So this is the ancestor of the particle x13. So this ancestor lives at time 2, all right? And what numbered particle is that? After resampling is the particle A13, is the ancestral index A13, all right? And again, this is, so again, this is the index, right? This is the index that defines the ancestor of x13. And what is this index in the particular case? Remember, I don't use the tilde here referring to the particles. I use the notation, the numbering before resampling. So what is the number of the particle that led to x13 is the second particle. So this index here is equal to 2. And how about this complicated notation here, right? So this is the particle at time n equal to 1, which is the ancestor of the particle at time 2, which is the ancestor of the particle x13 at time 3. Let me repeat once more. This whole thing here is the particle at time n. What particle, what number of that particle? Well, it's the number A2 with superscript A13. So it is the particle that is the ancestor of the particle at time 2 that was the ancestor of the particle at time 3 that had index 1. Okay? So you will have again to look at this in more detail on your own, but one way or another, this is one way to write the ancestral indices. If you want to find another alternative way, you can write it as well like that. At the end of the day, all of these are one and the same thing. Okay, so just in summary of the Bootstrap, particle filtering, you remember we start with an approximation at a weighted approximation at n-1. We resample, so some of these original particles don't survive. We propagate those with our dynamical model one step ahead. So these are the surviving ancestral paths that lead to this particle I at time n. And then, we weight these particles and we produce, after weighting, a Monte Carlo approximation of our target distribution at time n. So basically what you have is At each time you have this idea of resampling, propagating to the next time step, and then weighting the samples. Then you start doing this again. And as we emphasize, the cost of this calculation is independent of little n. And in part, what you saw today, this resampling process addresses the issue with the degeneracy of the weights that we discussed before. So this will allow you to actually go further in time. But as we will see in in a follow-up lecture, there are other issues that come eventually with this resampling process, because some of these ancestral paths, especially at early times, are going to kill themselves. So eventually you're going to have only a single path left on the early times, as n increases. Okay. You can do the same type of approximations again for the marginal, for example, of the y's. So you remember we had produced a nice formula that gave us an approximation of the marginal likelihood as a product of these conditionals. Now it turns out that these conditionals, I had given you the formula before, they're nothing else but the integral of the observation model at time n times that the one step ahead predicted distribution. And this one step predicted distribution for the Bootstrap filter, it's actually calculated directly. I give you here the Monte Carlo approximation. So if you plug it in there, you get that each of these conditional of y's given all the previous y's can be written like this. And if you put everything together, you actually do get that the marginal likelihood can be approximated as the product of these Monte Carlo approximations, the way that you see in this equation. This equation may look a little bit cryptic, because you notice I have P of y1 on its own, and then I have this product of these conditionals, let's say of y2 given y1, etc. But P of y1 can be treated the same way as these terms, because you can write P of y1 as the integral in dx1 of g of y1 given x1 times mu of x1, all right? And then you can write down a Monte Carlo approximation for mu of x1, and then you will get actually the same identical Monte Carlo approximation for P of y1. So that way you can put all together, and that's how you go here from the summation from k equal 2 to n to, a product from k equal 2 to n to a summation to a product from k equal 1 to n. So this equation, there's no typo, it is a correct approximation. Okay, so the great thing is, again, the computational cost only is controlled by the number of particles that you use. Of course, the memory requirements are proportional to little n times capital N. It turns out that maybe in a lot of filtering applications, you really don't care about the to compute the whole posterior of all the states given all of the observations up to time n, and maybe you are interested only on computing the marginal filtering distribution of xn given all the observations up to time n, or maybe, you know what, you are interested in some function of the states that somehow can be updated incrementally as indicated here, where you have some all the previous states are represented by this value Sn minus 1 if you like, and then the new evaluation of time n is really a function of this function Sn, okay, that depends, you know, on x1 to n plus this Sn minus 1. So basically, if you have an approximation that looks like that, right, you can actually reduce the memory requirements to the order of omega n, where n is the number of the the Monte Carlo samples. So the idea is, when you do marginal filtering the way that you see in this equation, the computational cost, of course, is proportional to the order of number of samples, but the memory requirements are also in proportion to capital N, because you don't need to keep in track in memory all the previous sample paths, as we have seen and discussed earlier. All right, this lecture has been much longer than what I anticipated, so let's rapidly move through the remaining of this lecture. What I have done is, just for your own information, for a linear Gaussian state space model, since we talk about these recursive filtering equations, I provide you the prediction and the update steps in an explicit format. So these are the equations. If you want to compare your simulator with the exact results coming from Kalman filtering, you can use these update equations. And again, everything is Gaussian. Any integrals that you saw before can be computed analytically. All right. Talking about this, recursive equations, can we write down a recursive equation to compute smoothing distributions? And remember, the smoothing distribution is, if I have all the observations up to capital time t, can I compute the marginal, let's say, of xn given all my measurements? So this is something that you will do offline. You will collect all your measurements, and then you say, what is the best now I can say about my state xn? And this smoothing distribution summarizes that. So let me give you what the bottom line result is. Suppose you have computed your marginal filtering distributions as you move forward in time, and also you have computed the one step ahead predictive distribution x of n plus 1 given all your measurements up to time n. And you have done this for little n equal to 1 to 2 up to your final time capital T. To compute then this smoothing marginal distribution, this distribution that you see here, what you have to do is you have to go backwards in time, starting from t minus 1 to t minus 2 all the way to time 1, and you're going to have to use the following recursive equation. So you notice here you have the smoothing distribution. This is the smoothing of xn plus 1 given all the observations, and here is the smoothing of xn given all the observations. And let's see what else is involved. This is your dynamic model, no big deal. Here, this is your filtering distribution that you computed moving forward in your recursion. And this is your predictive distribution, the one step ahead prediction that you also have seen in the previous discussions on the forward recursive equations. So effectively, we have a backward way to calculate this smoothing distribution. And you can see this calculation requires both the forward calculation and the backward calculation. For those who later on will take a course on probabilistic graphical models, you will see that there is a very nice and graphical interpretation of these forward and backward messages, as we call them, and how you combine them basically becomes very straightforward using probabilistic graphical representations. But again, all of them are represented here with the equation that you see on this backward pass step given by this blue equation. If you ask me how is that blue equation coming from, the answer is extremely simple. If you want to compute this smoothing distribution, you can plug in an xn plus 1 and integrate that thing out. And then keeping y from 1 to t constant, you can use the product rule. And this effectively, okay, so I have an approximation here that is not an approximation. Actually, it is, for the state space model, is correct using conditional independence relations. But this distribution that you get when you apply the product rule, you notice is conditioned on y from 1 to t, you can show that actually this is equal to p of xn given xn plus 1, comma y from 1 to n. Okay, the values of y from n plus 1 all the way to capital T are not affecting this distribution, so this is what you get. And then effectively what I have done here is I have used sort of the Bayes rule once more by reversing the order of xn and xn plus 1 by writing this as the dynamic model xn plus 1 given xn divided by the marginal of xn plus 1 condition on y1n, and then of course I have this filtering distribution. So again, this, what you see here, keep y from 1 to n constant and change the order of xn plus 1 and xn using Bayes rule, and looking carefully in the dependencies, this is what you get, and this is basically the equation that you see in the backward pass that we discussed a while ago. Of course, there is this equation here that I assume that is true. P of xn given this, somehow that y1 to t became y1 to n, and the question is why. My only suggestion would be for now, for this course, to be able to derive these relations, be sure you don't make conclusions simply looking at any arbitrary probabilistic distributions. Try to use forward information passing, if you like, and then use some common sense in the derivation. So you notice this is a backward calculation, so it is not immediately obvious that this is true. So if you want to actually make it immediately true, what you can do is you can split this y from 1 to t to two parts, y from 1 to n and y from n plus 1 to capital T. I can actually, I can actually keep this xn plus 1 and y1 to n constant in my conditioning, and then use Bayes rule to reverse the order of xn and yn plus 1 to t. So then I get the approximation that you see in here. And then notice what the obvious assumption is. When I look at the observations from n plus 1 all the way to capital T, I say, you know what, if I know the state at xn plus 1, I don't really need to know the state at the previous time xn, or I don't need to know the observations up to time n. Xn plus 1 contains everything that I need, and this is what I have here. And similarly, when I look at the denominator and I say, look, if I have my state xn plus 1, I don't really care about my previous observations to compute the probability of y from n plus 1 to t. And then you can see that this blue and this red probabilities cancel out, and effectively the statement that I had before is satisfied. The idea here again is to make this simplifications, you're going to have to use common sense, but my advice is for now, since you don't want to use probabilistic conditional independence relations, right? Use forward messages, messages where you know what causes what and what depends on what. Okay, and that's what I have done in this forward filtering, backward smoothing type of calculation. There is another backward calculation that is less common, and this goes with the name forward backward two filter smoother. And this new calculation requires to evaluate what's called a backward information filter. And a backward information filter is the probability of y from n to capital T. Capital T again is the end of my observations, given my state xn. And you can see the recursive relation. To evaluate this backward information filter, you need to know this filter at time n plus 1, that's what you have, and then you need to know, of course, your dynamical model and your observation model. And why do we need this backward information filter? Because this backward information filter, through the equation on step 2, can allow us to compute, to update and compute this smoothing distribution of xn given all my observations, and that smoothing calculation requires basically the backward information filter, all right, times the one step ahead, this is the one step ahead prediction, divided by this normalization factor that follows similar calculations with the one that we saw before when we discussed about the marginal likelihood. I am not going to give you the derivation. Actually, the derivation is already in the slide, and you may want to practice on understanding these conditional independence relations to show that these calculations are correct. I'm only going to say that this backward information filter is not actually a valid density in the sense that if you try to compute this integral may turn to be infinity, which means if you try to use this backward smoother to do sequential Monte Carlo approximations, those approximations may be completely invalid and may give you complete garbage results. Now, there is a reference that I give you in the slide that addresses a way to resolve this problem and still do sequential Monte Carlo on these two filter smoother. And that reference, what it does is it introduces an approximation to the marginal of the posterior at each time n. And again, you can consult this reference from 2008 to see how the problems with doing sequential Monte Carlo can be resolved for this smoother. All right, we have been a long way in this lecture, and I only have 3 or 4 slides, so if you can be a little bit patient with me so we can finish this lecture. So what I want to do in these 3 or 4 slides, I want to discuss on how we do inference, not only of the states, but maybe some parameters theta that define either the dynamic or the observation model or both of them. Okay, so can we do this? So I indicate these parameters here with theta. So my dynamic model has some parameters theta, and I use the same parameters for convenience to indicate also my observation model. All right, so to do inference, we need to compute the posterior of both x and y. We need to compute the posterior of both x and theta, given my observations y, and that posterior is the posterior of x given the observations y and theta times the marginal posterior of theta, and I call this marginal posterior because there's no x here, right? So this is the posterior of theta given my observations, and so this p of theta given y is nothing else but the marginal likelihood given theta times the prior on theta. Now, an obvious way to address this problem that somebody can think about is maybe, you know what, we can use all the Monte Carlo approximations we learned in the lecture today, but instead of using only inference on states, we can do inference on a new set of variables that involve both the states and the parameters. And this new extended space, the new variables, I call them z here. So z is, involves both xn and theta n. But you may say, well, how can you do this? Because theta n is actually not changing with time. And I say, well, mathematically, I can do anything I want to. I can define a transition model that actually forces theta n to be the same as theta n minus 1. So in the new space, my dynamical model looks like this, and the observation model is just a parameterized version of what we had seen in the earlier lecture. Now, obviously, trying to do inference using Monte Carlo with these approximations may not work at all. And, you know, this is an active area of research. You may actually start thinking of ideas. And I see here, because we put this subscript theta n, maybe you want to introduce, after all, some noise to the model theta n. Maybe you want to make theta n to be random variables. So there are lots of tricks that maybe you want to do this. But at the end of the day, if you want to compute static parameters, you're going to have to use one of your favorite techniques for estimating parameters. So you're going to have to use maximum likelihood. For example, maximize the marginal likelihood of y given theta. Again, the x's here have been integrated out. Unfortunately, this MLE problem doesn't really work because this marginal likelihood is multimodal distribution. So people have actually looked in using what's called the Fischer identity. So they use gradient descent algorithms, so stochastic optimization algorithms, and using the so-called Fischer identity to drive these algorithms. And again, what is very nice with this identity is the only information that actually you need to compute this gradient. This is a gradient again of the log of the marginal likelihood, but it's a gradient with respect to the parameters theta. The only information that you need is the unnormalized target posterior for a given theta. And remember, this is what we had before, plus our target distribution, the posterior of x given y, as a function of the parameters theta. So everything we discussed actually fits in nicely with this Fischer identity. And again, it is straightforward to actually prove this Fischer identity. You can actually take these gradients on the left-hand side and the right-hand side. And I think, if I remember, the only thing that you need is some marginalization that p of x and y, when you integrate in x, that I see here, gives you p of y. But apart from that, everything it is straightforward. So does the Fischer identity work? Of course, it works better than using maximum likelihood. However, it can be very difficult to scale the components of the gradient. But it is an algorithm that is, there has been a number of publications that use this algorithm that you may be able to find on the web. And so that's certainly something better than MLE. For those who know expectation maximization, you can actually use the EM algorithm to do this. And you remember in the EM algorithm, you can treat this states x as your hidden variables and theta as your parameters. So what you will need to do is you will need to have an estimate of the posterior of your hidden variables as a function of the parameters. So what I have here, I have the expected joint log likelihood of x and y, and the expectation is taken care using the parameters at the previous iteration. So you notice, so this is my expected joint log likelihood using this posterior evaluated at the previous parameters. If you write this explicitly, if you write down the normalized posterior term by term, you can actually see that you can express this joint log, expected log likelihood as this term plus this summation. And again, the great thing about what we have done today in our discussions on computing approximations to the joint posterior distribution is, you notice, what do you need to do this EM implementation of this for this problem? I see here you need, you need these distributions. And what are these distributions? Can somebody tell me? This distribution is of x1 given y of 1 to n. To me, this looks like a smoothing distribution, right? You use all your observations up to time n, and you are looking for estimating x1, so the distribution is a smoothing distribution. And here is also a joint smoothing distribution of xk minus 1 and xk, given all the observations from time 1 to time n. Bottom line, the expectation maximization algorithm can be applied extremely naturally in updating the parameters theta. It's a highly recommended algorithm, and I think a little bit more robust than using the Fischer there are many more important problems that somebody can discuss here. And let me just finish with the generalization. That's actually an active area of research. So remember, the dynamical model that we use looks like this, and this is our observational model. And before we took some Gaussian noise for these variables v and e. Now, up to now, we took very specific, simple Gaussian models for f and g, or, in many occasions, since I have not given you any examples yet, right, we didn't really say much about f and g, but you anticipate that f and g are parametric models the way we have seen them up to now. So there is a way to actually repeat a lot of the calculations that we discussed before, where now f and g, they're non-parametric models, and a particular class of non-parametric formulations that receives attention is using Gaussian processes to represent f and g. So f and g can be represented with some prior Gaussian process models with some covariance functions that you see here. That's a covariance function for this f and for g, and I indicate the parameters that define these covariance functions as zeta. So you can think of theta, for example, representing length scales in the kernels that define the priors for f and g. So the problem now becomes very difficult, because not only you have to estimate the posterior of the states, not only you have to estimate the posterior of the parameter zeta and maybe the posterior of your noise variables, maybe let's say the variances in your noise model, but now you have to compute the posterior Gaussian processes for f and g. Okay, so the joint posterior of f and g of the Gaussian variables, these noise variables q and r, and the parameter zeta in your kernels, and all of the states have to be computed simultaneously. If you are interested to read more about this, this has been a very active recent area of research, and maybe it's an area that may be of interest to some of you. You can look for ideas in the two papers listed on the bottom of this slide. So what I'm going to do is I'm going to finish here, and we're going to come back in 2 days with another lecture on sequential Monte Carlo, and in those lectures we will see a lot of examples and address some of the issues that still remain in our approximations. Thank you.